All right, settle down, settle down. Yeah, I know you're all dying to know about the second half of the lecture, about Riemann sums and how to approximate integrals underneath the curve. So I've gone through all of this just to recap what we learned about last time, because we have two more subjects to talk about in terms of the methods on how to approximate. So let's get over that really quickly before we move on to the new subjects. So we last left off about approximating a specific kind of integral, the one that will go from 0 to 2 for the function x to the third power dx. The graph is very nicely written over there. And so what we have is that we would need a table usually to list out all the values. If you remember from last time, is that we had 5 separate values selected for x because they requested that we do this in 4 sub-intervals. Again, that's 4 rectangles in the case for left and right Riemann sums. Again, 4 areas which we will add up to approximate the area underneath the curve. So going across, because we only go from 0 to 2, we had to cut that in half to 1/2 and 3/2 in order for us to get all the heights needed in order to start adding everything up. So from the results of last time, our left Riemann sum ended up with 9/4. Our right Riemann sum ended up with 6 1/4. Again, those approximations will change based off of the shape of the graph and whether that means we were under the approximation or over the approximation of what the actual graph looks like. Okay, and so from there, we have just 2 more methods to go over today, which will be the midpoint approximation and then the trapezoid approximation. Okay, so not too bad. Everything is meant to be using simple geometries just for us to be able to approximate or get an idea what it looks like underneath the curve. Okay, so let's begin here first with the midpoint approximation. Okay, so we are looking down the line here to see that, okay, well, if left and right are far beyond any sort of approximation that will help us out during this time, especially with how rectangles don't fit very well with such a heavy curve based off an x cubed graph, why don't we split this in half one more time? That's why it says midpoint, to split this in one segment in between each of the ones that we already have to see if those heights will be better representation of what we have. Okay, so what that usually means with midpoint is that because we already selected these 4 as subintervals, again from the distances from 0 to 1/2, 1/2 to 1, 1 to 3/2, and 3/2 to 2, right? We can split them one more time down exactly the middle and use that as the height. Now, one thing to note is that we still are looking for 4 subintervals that were of equal base length. And so the actual bases won't change. We're just now deciding where the function will take us on the heights of each of those points. So what that means is that we actually need to continue with a separate table here of understanding. Now, instead of going from 0 to 1/2, instead we can go take it the other way now. Okay, and where we can now say, all right, how about 4 separate times we're going to split in between? So now instead of saying 0 to 1/2, what if we split that in half one more time? So now we have x of 1/4, then splitting between 1/2 and 1, that's going to be 3/4. Then going from 1 to 3/2 will be 5/4, and lastly 3/2 to 2 will be 7/4. Okay, something to note, of course, with the midpoint approximation is that the distances between any 2 bases are exactly the same as well, still at a 1/2 base length, which is exactly what we had for our previous summations. And now we just need to plug in then for the function itself to see what those new heights will be at those midpoint approximations. So to begin with, our new f of x result will be 1 to the 64th power, because that's 4 raised to the 3rd power. Looks like that will be a common way all the way through as a denominator. Then 3/4 raised to the 3rd power is going to be 27/64. 5 raised to the 4th power is 125/64. And then lastly, 7/4, if you remember here, is going to be the, I had it written down here for a second. Yes, 343 over 64. No need to worry about these crazy calculations as of right now. It's just a result of raising the third power for each of these guys. Okay, so we have these 4 new heights for us, and thankfully the bases are all exactly the same. And again, the idea is that we are looking to draw, instead of a rectangle from either 1 or 3 halves, we're looking to draw a rectangle right down the middle, again in between those 2 points, and then extending out a new rectangle on either side, and then taking the area as such. Again, for each of these ones, we are doing that for either side. So with that, we should be getting a little bit more of an accurate representation, although there are still areas left over that are not covered by rectangles, or there are spaces as well where the area has gone over the curve. But again, these are all approximations to see whichever way we can get close to the answer without us actually knowing exactly what is needed for the function. Okay, so because of that, let's go on and let's calculate for the midpoint approximation, and let's see what we end up with. So similarly as before, the base is exactly 1/2 across all 4 rectangles, and now the heights will be as follows. So it's be 1 over 64 as we have on our table, then it's going to be the 27 over 64, and then it's going to be 125 over 64, and then the last is be 343 over 64. Okay, so again, these are the 4 different heights, all multiplied by the same base. So all we really need to do is just to be able to get through these calculations fairly simply. Okay, but thankfully again, I have this all written down right here, just so we can make sure we have the setup there properly, and the calculations will be just taking a few extra minutes for us just to make sure we end up with something reasonable. So we end up with 1/2 multiplied by 496 over 64. Saves us a lot of time to do just some simple arithmetic here to just add up to something that ends up with something like this. So we just need a few more steps to simply make this fraction look more palatable for us. And so with that, we'll end up with the result of, by multiplying that 1/2, will be the 240 over 64. And then we can start factoring out some easy numbers. For us, at least, we can factor out a full 8 from both the top and the bottom. It gives us as 31 over 8 as a result from that. And then we can get to our mixed number form of 3, that was almost 4, and 7/8. That's right, so it was almost 4, but right there below as the total area using midpoint approximation. So we can list that down as one of the answers for this whole set of problems. All right, and so again, the idea here is that we are actually putting together for the midpoint approximation, again, some ways at least for us to realize that we're dealing with the midpoint method of approximating underneath the curve, where again, we're dividing even more so on 1/2 of each of the different points that are set out, again, cutting it in half one more time, such that we can get to a little bit more accurate of a response. Again, that is a little bit more than the left Riemann sum at 2 1/4, and then the right Riemann sum at 6 1/4. Okay, so I think with that, we should be good enough to move on to the trapezoid approximation. So let's just clear the board like this. And so we have everything ready for our next and last approximation method, the trapezoid approximation. Trapezoids? Who cares about that? Well, for one, think of it like this. What if instead of using straight rectangles, we can swap it over, this is the wrong color, but we swapped it over to a more reasonable shape that will match a bit more for what we're dealing with over here. With instead of a rectangle, we take the 2 heights between the 2 points, and then imagine instead we went diagonally. Oh, that's right. We can take a method to actually go diagonally across each of the sections here, such that As you can see, we become even more accurate than before. Now, the main issue, of course, is that we still have some areas underneath that are not exact to the curve because we're dealing with straight lines here instead of curves. But nonetheless, though, the next question is now going to be, well, how do we find areas of trapezoids, right? Well, maybe people weren't that unfortunate enough to not pay attention in geometry class. Nonetheless, though, this should be fairly simple. Think of it this way. Instead of a rectangle, again, we have a trapezoid that's going to be usually in a shape of something like this to match the curve, right? We have everything that matches with the rectangle. It's just that we got that little bit of a triangle that comes across. Or you can also look at it this way for the same trapezoid, that we have the triangle that has been cut away from the actual shape itself. In any case, though, the way that we should be able to do that is that we don't need to do triangle and rectangle added up. No. That's way too much. We got a much easier way. With this kind of a trapezoid, all we need to think about is that we can cut that diagonal across in half one more time. And mathematically, we should be able to replace what we have missing with the one that we have extra when we cut that in half. And you realize that, well, if that's the case, for each of the heights across the trapezoid, because there's two different heights for this one that's measured in the vertical sense. Well, if we want to cut that in half and get the full area, that's all we need to do to find the area of this trapezoid is as if it's a rectangle with two different heights that we need to take the average of. So, just as a reminder here, the area here is going to be represented by the two heights, height 1 and height 2, all divided by 2 to take the average of the two of them, and then multiply it across the base as if it were a rectangle. Very straightforward. And that's pretty good because now with trapezoids is that we no longer need to do any sort of additional cutting. We just think of it now as each set of two heights that we just simply need to go across, which also means that we no longer need to go decide whether it's left or right, because we have out of 5 different heights, we can easily take in the 4 different rectangles, and then we just need to take the average between each set of 2. I think that's pretty good if you ask me. And so with that, the total area that we're dealing with is going to be, again, the base will still be 1/2. It's still 4 equal subintervals across for this function. So the base across all of them will still be 1/2, makes our life much easier. And the fact that we just need to go across now and say it's 0 plus 1/8 all over 2, added with the next step of 1/8 plus 1 all over 2. And then it's the 1 plus 27/8 all over 2. And then lastly, the 27/8 plus 8 all over 2. Just like that. So each set of the heights going across to 4 subintervals is pretty easy for us. Then, by just making sure we add everything up properly, again, keeping all the denominators. This time looks like the denominators will be 16 for now with an 8 over a 2 like that again. So for what I have, it's going to be 1/2 multiplied by 136 over 16 to get started with. Okay, then we can simply go ahead and start reducing some of this business right here in single steps. Will be 68 over 16, and then lastly we end up with the improper fraction of 17 over 4, ending us with a 4 1/4 total area using trapezoid approximations. Again, the main purpose is that you should understand how we got that area of each of those different subintervals, and then utilizing the table of values once more in order for us to find that out. So if we were to take a look at the comparison of all of these, as you can see, we have a little bit more accurate approximation methods of midpoint and trapezoid that are a little bit more sophisticated than just taking left or right sums. But nonetheless, though, these are all the 4 different ways to actually approximate a definite integral of a function. Again, for the most part, we actually wouldn't need to know the equation of the function. If they literally just gave us only the table of values, we can then find the rest of these without a problem. Now, The main issue though, of course, is that, well, sure, we approximated all this, but how close is it to the actual value, right? So for a lot of times, we can either go one of two ways. One, you can shove things into a calculator and find that out, but where's the fun in that, right? We can very easily, because they gave us, thankfully, the definite integral already, we can take the actual integral and see what that looks like to the original result versus our different sets of approximation methods that we just learned today. So this should be very simple. An integral of x to the third power. Well, let's just see if we can fit it down here again. So x to the third just means that we need to bump it up to x to the fourth, and then we take a 1/4 coefficient to knock out the power rule that's coming down. We'll evaluate it from 0 to 2 as the limits. Then with that, we have 1/4 as a coefficient waiting for the evaluation of the limits of 2 raised to the 4th power minus a 0 raised to the 4th power. Okay, and then lastly, we'll have 1/4 multiplied by 2 to the 4th being 16, which will be a total 4 waiting for us as the actual area underneath this curve. Okay, now that seemed a lot simpler, thankfully, because we've been working so hard on integrals. But again, there will be times on the exam where they wouldn't give you this at all, just not existent. They'll just tell you, here's a graph, here is some table values, go and approximate, why don't you? And that's usually how things go on the exam. But at least in the case for what we have so far, if we were to really take a scrutinous eye underneath all of these, you'd see that the midpoint approximation in our sense was the most accurate to the actual with a slight under approximation, while the trapezoid was just a little bit worse of a slightly over approximation to the actual amount. Again, as you can see, using big blocks of rectangles to try to approximate something with a large curve like this isn't very accurate. But again, it's all just ways to see how we can approximate an area underneath the curve. Okay, and so with that, that will conclude our first lecture about Riemann sums. Again, split up into 2 parts here. Tomorrow we'll go over another set of example problems. And then from after that, we should be able to continue through our series of understanding how to use definite integrals to our advantage. As always, you can email me at labcoatmath@gmail.com. Again, I can put it right there. As well as today being the Thursday where we film this, is that I will be live from 4 to 7 p.m. Pacific time. If you have any questions you'd like to ask live, or I'll be going over all the ones that are sent to the email if you have any there as well. All right, so as always, thank you very much for watching, and we hope to see you next time.